Welcome on and all to the Math Magic Show. In this one, let me motivate the rational roots theorem through an example, and then we'll take a look at an application. So imagine you have already two roots, x equals 3/5 and x equals 2/7. Imagine these are, for example, two roots that you've gotten from solving an equation, like a quadratic equation. Starting with the roots, you can rebuild the equation piece by piece by piece. So how does that work? Take a look. For example, I could do this. I could take x equals 3/5 and I could multiply both sides by 5. That would tell you that 5x equals 3. Then I could take that 3 and I could move it to the left side with subtraction, so that would tell you that 5x minus 3 equals 0. From there, what I can conclude is that 5x minus 3 is a factor, say, of my quadratic equation. So again, I'm motivating the rational roots theorem. I'm beginning with the roots and I'm working back towards the equation, just so we're clear on that, okay? And you'll see in a second why I'm doing it this way, a very specific way. Okay, let's now also begin with the other roots. So, the other root is 2/7, as you can see. Let's work backwards. I'm going to have 7x equals 2, so I multiply the first step by 7. So 7x equals 2. Then I take that 2 to the left side with subtraction. So I get 7x minus 2 equals 0. So that 7x minus 2 is what you would get from solving, say, a quadratic equation and factoring. So in other words, the factor would be 7x minus 2. So I've begun with the roots and I've rebuilt my factors from the roots. Now let's think about this for a second. Let's multiply these factors. So in other words, to continue rebuilding my original quadratic expression, for example, or equation if you like, I would say that it's 5x minus 3 multiplying 7x minus 2. Okay, I'm being a bit loose here with expression and equation. The goal is to just look at this part right now. 5x minus 3 multiplying 7x minus 2. So let's FOIL this out. So I'm going to have the following. I'm going to have 5x times 7x. That would give you the 35x squared that you see. Right here, 35x squared. Then I would do 5x times negative 2. That would give you the negative 10x that you see. Then I would have negative 3 times 7. That would give you that negative 21x that you see. And then I would have negative 3 times negative 2, which would give you that positive 6 that you see at the end. But let's now do something that perhaps is a bit unconventional. In other words, take a look. Let's rewrite. So we write the 35 more clearly as 7 times 5. So I've done that over here. I'm rewriting the 35 as 7 times 5. And more than that, I'm rewriting the 6 as 2 times 3. And now, why would I take this seemingly unnecessary step? The goal, remember, is to motivate the rational roots theorem. Let's try to understand where it kind of emerges and why it exists and all that. So, look very carefully now at some key pieces of information. Let me move on to the next page. Imagine this is the same as in the last slide, but enlarged, obviously. And there's a 7 multiplying a 5. That's the 35. And here there's 2 times 3, which is the 6. So now let's take a very careful look at one of the roots. Imagine this root, the 3/5. Now look at this as an example. The 5 that is in the denominator of that root, as you can see, it comes from being a factor that is a member of this product right here, 7 times 5. So the 5 is there, and the 3 that you see there, that comes from the 3 at the end, you see? So that is 3/5. In other words, the numerator of the root, is a factor of the last term, and the denominator of the root is a factor of the leading coefficient there, the 5, see? That's telling us a story. Let's do this for the other root also. So again, imagine the other root is 2/7. Let's go through this carefully. You can probably already see the story anyway, but that 7 that is in the denominator, as you can see, is the other factor of the 35. And then the 2 that you see in the numerator, that's the other factor of the 6 at the end, in other words, the 2. So again, the story is that this root of 2/7 takes a factor from the last term in the numerator and a factor from the first leading coefficient in the denominator, the way I'm pointing here with the arrows. So I've shown you this using a relatively simple example that involves, for example, only an x squared kind of quantity. But now let's actually take a look at it, perhaps in a slightly more sophisticated way. So here it is. Imagine we have 1x cubed plus 2x squared plus x plus 3. And I want to write down a list of the possible roots of this expression. In other words, the values of x I would plug into this expression to make it have the value 0. So I apply what I've just learned in an example. I'm going to first look at the factors of the 3 at the end. So there's a 3 above my head. And the factors of that number would be the following. -1, 1, 3, and -3. Why is that the case? Because 3 divided by -1, no remainder or anything like that. 3 divided by 1, no remainder. 3 divided by 3 is 1, no remainder. 3 divided by -3, again, you see, not a problem. That's a way to think about it. So now let's take a look at the next one. You have to also look at the factors of the leading coefficient. So as you can see, the leading coefficient is the constant on x cubed, so the 1 in other words. So that has very easy factors, 1 and -1. Those are pretty much the only two numbers that go into the 1, the coefficient of 1 on x cubed. So now let's think about this a little bit as follows. What are the possible rational roots? Just like in the previous example, we saw that the rational roots were formed by taking factors of the last term and dividing by the factors of the first term. We'll apply exactly the same concept here. So let's carry that out. So first, what do I have here? I have -1 over 1. In other words, I took the -1 from right here, the factors of 3, and I divided by the -1, which was, for example, the first factor of +1. So that's from here. And that gives me a 1. This 1 that you see right there, that +1, that represents a possible root. In other words, it's possibly a value that you could plug into the expression and make the value of the expression 0. Okay, that's what it means. Let's take a look at the next one. So imagine I take -1 over +1. Okay, so again, what I'm doing here is the following. I'm taking the -1 that you see kind of above me there, and I'm pairing it with this +1 that you kind of see above me now. So that -1 divided by this +1 gives me this output of -1. In other words, what it's saying is -1 is a potential root. If you plug it into the expression, potentially it could be equal to 0. Okay, so this is just the beginning though. Let's continue. Next, I'm going to take the 1 that you see directly above my head, and I have to now combine with the -1 and the +1 that are the factors of the 1, the leading coefficient. So when I do that, it's going to look like the following. 1 divided by -1 is -1. Then I repeat that. I'm going to have 1 divided by 1, which is 1. Okay, I hope you've got all of that. Now, when you looked with these numbers, I hope you see something happening, which is that clearly the values are repeating. So when you make your final list of rational roots, possible rational roots, you want to make sure you just write it down one time and that's enough. Okay? Let's continue though, because this is not done. So next stage. You take that +3 and you gotta pair it as follows. With the -1 above my head and then with that +1 above my head. It has to be paired with each of those values. Now in books, they will write this somehow, sometimes with like a plus or minus, and it gets kind of complicated and complex looking. And that's fine, but you gotta, I think, go through this simpler example first. Then you can decipher the meaning of the symbols more easily. That's how it was for me at least. So what I'm gonna do is I'm gonna take the 3, I'm gonna divide by the -1 as a first step. So 3 divided by -1 gives me -3, meaning that -3 is a potential root of that expression, okay? Okay, then I take that same 3 and I divide it by +1. So 3 divided by 1 is 3, meaning that 3 is a potential root. I then continue. I'm going to take the -3 and I'm going to pair it with the -1 and the 1. And that's going to give me 2 more potential choices. So let's carry that out. I will have -3 divided by -3, which is +3, but you see that already is repeating. And then also -3 divided by +1 is -3. Again, that is repeating. So when I look at this list of potential rational roots, I have a 1, a -1, -1, 1, -3, 3, 3, and -3. Obviously they're repeating, so for that reason, in the final form, to answer the question, what are the potential rational roots of this expression, I would simply put -3, -1, 1, and 3. So put them down unique. Only once, in other words. And that is it for me. I hope this little journey of ours has given you some insights. Perhaps you have learned something new. I always hope for that. Thank you so much for watching. Please leave a like and subscribe, and I will see you in another video.